Good day everyone. I am Marc Cacatian with my groupmate Cielo Angela Advincula, and for our final output, we will be discussing the rate law. The rate law is under the study of chemical kinetics, which is a study of how fast a chemical reaction occurs.
There are factors that affect the rate of chemical reaction, namely the concentration of the reactants, surface area, temperature, and the presence of a catalyst.
What is rate law? The rate law determines the connection of the rate of the reaction to the rate constant and the concentrations of the reactants raised to some powers. Or in simpler words, it shows that the reactant concentration affects the rate of chemical reaction.
For the chemical equation shown on the screen, the rate law is given as rate is equal to K times A raised to the power of X multiplied by B raised to the power of Y, where the capital A and B represent the concentration of the reactants and K is the rate constant. The rate constant K is the proportionality constant relating the rate of the reaction to the concentration of reactants and is independent of the concentration of the reactants and pressure.
The exponents x and y are the orders of the reaction with respect to the reactant that they are assigned. Exponent x is the order of reactant A, while exponent y is the order of the reactant B. It is worth noting that the exponents x and y are always determined experimentally and are given in exams, and the stoichiometric coefficients of the reactants do not affect the order of the reactants in any way.
There are different orders in the reactants of the rate law. The most common are the 0th, 1st, and 2nd order. Also, the overall order of a chemical reaction can be obtained by adding x and y. In a 0th order reaction, the reaction rate does not depend on the reactant concentration. The rate law for a 0-order reaction is expressed as rate is equal to K, since if you raise the concentration of the reactant by 0, it becomes 1. Rate constant K multiplied by 1 is still K, hence rate is equal to K. The rate constant K of a 0th order reaction is usually expressed as K is equal to m over S.
A first order reaction occurs when the reaction rate is proportional to the concentration of the reactant. For example, if you quadruple the reactant's concentration, the reaction rate is also quadrupled. The rate law for a first order reaction is expressed as rate is equal to K times A, wherein x is equal to 1. The rate constant K first order reaction can be expressed as either K is equal to 1 over S or K is equal to S raised to negative 1.
A second order reaction is proportional to the square of the concentration of a reactant or the product of the concentration of two reactants. It can be expressed as rate is equal to K times A raised to the power of 2, wherein x is equal to 2, or rate is equal to K times A times B, where x and y are both equal to 1. The rate constant K for a second order reaction can be expressed as either 1 over m times S or m raised to the power of negative 1 multiplied by S raised to the power of negative 1.
For any nth order reaction, the rate constant K can be expressed as m raised to n minus 1 times S raised to negative 1, with n being the overall order of the reaction.
Take the sample problem as an example. For the chemical equation shown on the screen, the rate law would be as follows. The following data were also collected as seen at the table presented. Determine the order of each reactant, overall order, rate constant, and the rate of the reaction when concentration of nitric oxide is 12.0 times 10 raised to the power of negative 3 m, and the concentration of hydrogen gas is 6.0 times 10 raised to the power of negative 3 m.
Given the experiment's results, we can compute for the order of each reactant. If we look at the table, we can observe that in experiments 1 and 2, when the concentration of nitric oxide is doubled while retaining the concentration of hydrogen gas, the ratio of the rate of reactions is approximately equal to 4. If we equate the two experiments as the following equation, we can cancel the K, quantity 2 times 10 raised to negative 3 raised to y, and we will be left with the equation 4 is equal to 2 raised to x. We can solve this by using the logarithmic equation log 4 to the base 2, which will give us 2. Therefore, now we know that the order of nitric oxide is 2, and we can write the rate law tentatively as the following.
To find the order of the other reactant, we perform the same procedure. But now we use experiments 2 and 3 because the concentration of hydrogen gas is changed, while retaining the concentration of nitric oxide. In these experiments, we see that the rate of reaction doubles, and if we equate the ratio of the two experiments as the following, we can cancel k and 10.0 times 10 raised to the power of negative 3m raised to the power of x, and we will be left with the equation 2 is equal to 2 raised to the power of x. If we equate it into a logarithmic equation, we will get log 2 to the base 2, which will give us 1. Therefore, the order of hydrogen gas is 1, and we can write the full rate law as the following, where x is equal to 2 and y is equal to 1. To get the overall order of the reaction, we add 2 and 1 to get 3. Therefore, the overall order is 3.
We use the following formula to find the rate constant. Plugging in the values from experiment 2, we now arrive at the following equation. And we get 2.5 times 10 raised to 2 m raised to negative 2 times s raised to negative 1.
We can now solve for the rate of the reaction when NO is equal to 12.0 times 10 raised to the power of negative 3m, and H2 is equal to 6.0 times 10 raised to the power of negative 3m, by using the rate constant we solved for beforehand using the rate law. Plugging in the given reactant concentrations and rate constant, we have the following equation. Inputting the equation into our calculators, we get the following answer. Rate is equal to 2.2 times 10 raised to the power of negative 4 m over s.
We hope you learned something new with our presentation. Thank you for listening.